This is an interesting study that's a nice complement to what we discussed in terms of state of CO2 removal. This one focuses on diverse carbon dioxide removal approaches, saying they could reduce impacts on the energy, water, land system. Could reduce, its keyword. They are being humble, arguing that there is ways to reduce the impacts, but we don't know for sure. They could reduce the impacts, right? Reading their abstract, carbon dioxide removal is a critical tool in all plants to limit warming to below 1.5 degrees C, but only a few CDR pathways have been incorporated into integrated assessment models that international climate policy deliberations rely on. The integrated assessment models we have discussed in other podcasts are used for projections into the future, sometimes iterating with the Earth system models or the climate models in terms of converting the representative concentration pathways into various impacts on the shared socioeconomic pathways, for example. A more diverse set of CDR approaches could have important benefits and costs for energy, water, land systems. Here we use an integrated assessment model to assess a complete suite of CDR approaches, including bioenergy with carbon capture and storage, afforestation, direct air capture with carbon storage, enhanced weathering, biochar, and direct ocean capture with carbon storage. CDR provided by each approach spans 3 orders of magnitude, with deployment and associated impacts varying between regions. Total removals reach approximately 10 gigaton CO2 per year globally, largely to offset residual CO2 and non-CO2 emissions, which remain costly to avoid even under scenarios specifically designed to reduce them, right? So there will be residual CO2. In other words, even after we have reached all our renewable energy goals, electric vehicles and so on, and maybe even reduce consumption, you are going to have irreducible emissions of CO2 and non-CO2 emissions. So essentially you will need CDR to remove residual emissions to reach net zero and completely decarbonize the system. Their scenarios are built this way in the integrated assessment model. Emissions and removals. Total greenhouse gas emissions continue to increase in scenario 1, reaching 80 gigaton CO2 equivalent per year by 2100 and resulting in approximately 3.5 degrees C of warming relative to pre-industrial levels by 2100. So gigaton CO2 equivalent again is converting non-CO2 greenhouse gases into CO2 metric by using their global warming potential, as we have talked about elsewhere. CO2 emissions reach net zero around 2045 in scenarios 2 and 3, but total CO2 equivalent emissions from all GHGs remain net positive for much of the century. So just focusing on carbon dioxide removal, we are still carrying non-CO2 greenhouse gases. Non-CO2 greenhouse gases comprise 55% of residual emissions in scenario 2 and 60% in scenario 3. So after having reached your goals, you still have residual emissions, of which 55% or 60%, depending on the scenario, can be from non-CO2 greenhouse gases. Total gross CDR is approximately 12 gigaton CO2 per year by 2050 in scenario 2 and 10 gigaton CO2 per year in scenario 3, which we'll see in a minute. The assumed limit on bioenergy in scenario 3 reduces the share of BECCS bioenergy and carbon capture and increases the share of DAC's direct air capture and land use negative emissions compared with scenario 2. Lower DACs and BECCS deployment, especially in the second half of the century in scenario 3, reduces the cumulative CDR amount by 16% through 2100 compared with scenario 2. Scenario 3 also reduces geologic carbon storage rates by approximately a factor of 2 relative to scenario 2 in 2050, with greatest decrease in carbon capture and sequestration from fossil fuel electricity. Okay, keeping all that in mind, let's look at the overview of CDR technologies modeled in this study. It's bioenergy, carbon capture and sequestration. Some details here. Afforestation, direct air capture with carbon capture and sequestration. So solvent and sorbent based processes using a combination of electricity and natural gas to separate and geologically store CO2 from the atmosphere. Enhanced weathering, so crushed basalt there. Biochar, slow pyrolysis of second generation biomass, so it details matter in terms of where the biomass actually comes from and whether the energy used for producing biochar still produces net zero or net negative emissions from biochar application. DOCS, direct ocean carbon capture, electrochemical stripping of CO2 from seawater paired with geological storage in a standalone plant or co-located with water desalination facilities. Keeping all that in mind, we'll go through some figures that are fairly detailed and complicated. So we're looking at emissions in gigaton CO2 per equivalent here, negative numbers here, and positive numbers up here with all these sectoral color codes going from flue gases, methane, N2O to transportation, industry, electricity, buildings, and then you have negative or beneficial effects, land use change CO2, biochar, biomass to H2 with carbon capture and sequestration, bioliquid refining, bioelectricity, enhanced weathering, direct air capture, and direct ocean capture. So you can see that positive and negative CO2 emissions in no climate policy, you basically remain positive with net CO2 and the addition from non-CO2 greenhouse gases, reaching 80 gigaton CO2 equivalent by 2100, as we said in the previous slide. To reach below 1.5 degrees C in 2100, we have to start, already we are behind in terms of going negative with these various carbon dioxide removal approaches. To remain below 1.5 with sectoral strengthening, you can see that there are some additional factors involved in these scenarios. So keeping these in mind, BECCS, where are the potential sites? So in millions of tons of CO2 with various scales, greenest being highest, 400 to 1,336 million tons. So you can see that China, India, and Southeast Asia need to do a lot. US, Greenland shows up here as well. And land use change, obviously there will be also reductions needed in terms of million tons of CO2, where you reach net LUC storage when you reach the higher numbers, but if you're in the positive range, then you have net LUC emissions. So there are some that still have net LUC emissions, which is not good news. But if you then go to direct air capture, you need, these are the numbers, maybe we should read the caption first. CO2 emissions and removals. Positive and negative annual CO2 emissions. Flue gas refers to halocarbon gases with very high global warming potential. In B to G, we are looking at negative CO2 emissions by CDR method and GCAM region in 2050. GCAM is the integrated assessment model from the US that's used in this study. LUC, land use change. The items on the charts appear in the same vertical order as in the key. Greenland is plotted as part of the EU 15, so it's numbers that show up on Greenland are because of the EU being a region within GCAM, which includes Greenland. Mongolia is considered as a part of GCAM's Central Asia region, but does not have meaningful data on direct ocean capture potential. Land use change CO2 emissions are reported as the net of afforestation minus any deforestation in each region into the future years. In some regions are projected to have net positive land use emissions in 2050. The fossil and industrial CO2 emissions constraints in both 1.5 degrees C scenarios in 2 and 3 are the same, but reduced non-CO2 emissions in scenario 3 lead to lower end of the century warming. Okay, so the non-CO2 greenhouse gases are reduced there. So just keep in mind that there are regional differences and dependence on the CDR method as well in terms of how much CO2 can be drawn down by 2050. So here are direct air capture. These are again promises, technological promises, and they're assumed to be working and scalable by 2050. Enhanced weathering potential. China, India, US, and some parts of South America and Southeast Asia have high potential in terms of millions of tons, going from 400 to almost 1 billion tons. These numbers here remain small. The orders of magnitude differences in each is obvious here. So land use change can only give you minus 205 to minus 100 million ton of CO2, for example, whereas direct air capture will only give you maximum of 32 to 41 million ton of CO2. Enhanced weathering, on the other hand, can give you 400 to almost 1 billion ton, as I said, and BECCS is assumed to give 400 to more than 1 billion ton, 1.3 billion ton here by 2050. Obviously, we are relying on these technologies and innovations able to scale up and meet our demands or needs in this case. Biochar, very small, 20 to 70 in the maximum in terms of million tons of CO2. Direct ocean capture has fairly big potential, 250 to 1146 kilotons of CO2, so you have to be careful. So it's very high for the Middle East, high for the US, and moderate for various other regions. You have to understand the details and the assumptions that go into these calculations to see why these numbers are so different and distributed the way they are. So looking at further, let's read the caption again first. Primary and final energy impacts. Global primary and final energy consumption by end-use sector in A, proportions of primary and final energy for CDR in 2050 in B and C. The items on the charts appear in the same vertical order as in the key. Following IPCC reporting convention, we report non-combustion energy sources as direct equivalents, while fossil fuels and bioenergy are reported in their primary energy content. So there are some details there that matter, which you should read up if you are interested in such details. Under this convention, renewable electricity may appear smaller and bioenergy larger in reported primary energy shares. So you have to keep that in mind as well. Okay, so primary energy and final energy here in terms of exajoules per year, the scales are different, so be careful there. This with no climate policy, and you are looking at energy for DAC and process heat, biomass with CCS or without CCS, renewables, nuclear, coal CCS, coal disappears at some point in the 2030s or later. Coal with CCS, oil with CCS, natural gas, and natural gas with CCS. And here you have biomass, hydrogen, electricity, district heat, gas, refined liquids, coal, electricity for CDR, and gas for CDR. So energy is still required for CDR, but the idea is that we will always be net negative, okay, or net zero in terms of overall carbon emissions and greenhouse gas emissions eventually. So I won't go into the details, but you see that there are various combinations for various scenarios. If you have no climate policy, energy consumption will go up tremendously, and here will be the final energy in exajoules per year, and this is for below 1.5 degrees C. It has to come down and rely more and more on renewables and less on coal. Of course, here coal remains all the way into 2100. For below 1.5 degrees C and sectoral strengthening, you have to increase renewables by quite a bit, with BECCS also playing more role, and coal will disappear, oil will continue, but there will be also natural gas with CCS and so on. So these are scenarios. You always have to worry about the uncertainties and the impact of various assumptions and the combinations of CDRs used here. So keeping that in mind, fraction of primary energy consumption from BECCS to keep below 1.5 degrees C in 2100. Here you have various levels of primary energy consumption from BECCS. So some countries and regions have very high, so EU comes up with very high in terms of use of BECCS. Parts of Africa, China comes up big on its percentage, 20 to 27% are these darker colors here, and some parts of Southeast Asia as well. These kind of sharp divides in New Guinea and East Timor, for example, have to be kept in mind, that they are partly also the way model creates regions and assumes the details on the potential for bioenergy and what they can contribute in terms of staying below 1.5 degrees C with their exploiting their BECCS potential. Looking at fraction of final energy consumption for DACS, enhanced weathering and direct ocean capture to stay below 1.5 degrees C in 2100. Again, various percentages here. You can see these are relatively small in terms of energy consumption for these CDRs, which is a good news. So you have some countries here consuming 2.5 to 3.5%, but the rest of them remain in smaller ranges from less than 0.5% to 1.5 to 2.5% and so on. So again, keep that in mind, that these are integrated assessment models which have gross scales of representation in time and space, but they are the best tools we have. And there are criticisms about these models. I have a podcast on why some people argue that these are not the best tools, but nonetheless they are used extensively both in IPCC and in studies like this. Global land area, so reading the captions here, land use impacts A to D, global land use and regional land use impacts of CDR in 2050 for scenario 2. The items on the charts appear in the same order as before. Note that proportions shown on the maps of biochar utilizing cropland and bioenergy crops are not mutually exclusive. So you could be having biochar and bioenergy at the same time. For example, bioenergy and other cropland may also deploy biochar. So biochar enhances soil carbon and affects soil properties like soil moisture retention, erosion, crop yields, nutrient retention, etc. So you have various contributions here again for these three scenarios. In scenario 2, by 2050, where do we end up? Bioenergy crop cultivation, forest, food crop, pasture, grassland and shrubland, non-food crops and other arable land. So you can see the various contributions, with forests being a prominent contributor, as well as grasslands and shrublands, pastures, with smaller contributions coming from food crops and so on in terms of impacts. So obviously we need to protect, restore and manage forests and grasslands, especially when we want to do bioenergy crop cultivation, to also avoid impacts on water and also food security. So you cannot drive bioenergy focused on CO2 drawdown and make life worse in terms of food security and water security for the poor people, for example, in the global south. Biochar cropland impacts to stay below 1.5 degrees C in 2100. These usually come with the probability. So below 1.5 degrees C in 2100 with a probability of 67% or 50% and so on. Okay, fractional biochar cropland in 2050 for this target. So you see some regions of the US show up, the breadbasket here. Large parts of India show up with 10 to 26% of fractional biochar over cropland by 2050. Similarly, higher numbers here over Indonesia and parts of Philippines as well. Bioenergy cropland to stay below 1.5 degrees C in 2100. Impacts in terms of fractional biomass cropland by 2050. Again, there are overlaps here as mentioned, because you can have biomass being grown with biochar applications as well. So again, various regions light up in terms of the percentages by 2050, 10 to 17% being the highest here in South America, parts of Europe, Mongolia and so on. Okay. Change in forested land area to stay below 1.5 degrees C, so fractional change. You need significant changes over parts of South Asia, 1.0 to 9.6% between 2015 and 2050. So take these numbers as you wish in terms of uncertainty. Small parts of US, such granularity, you have to make sure where it comes from. For example, here in the northwest corner of Africa, why does this show up to be having a large impact in terms of fractional change in forest cover? Is it climate driven? Is it human action driven? Or is it driven by CDR assumptions made here and so on? And Southern Africa shows up big, Madagascar does, large part of India does as well. So keep those things in mind. Here we are finally looking at water use impacts, global water consumption by end use sector, and desalinated water production by technology. Items are plotted on the charts in the same vertical order as they appear in the chart keys. Water consumption for bioenergy crop irrigation is shown, BECCS electricity included in that, and DAX process water by GCAM regions as a proportion of the total water consumption. Finally, desalinated seawater and groundwater as a fraction of total water withdrawals by GCAM water basin. So again, no climate policy below 1.5 degrees C, below 1.5 degrees C plus sectoral strengthening. So additional drawdowns done that way. So here is consumption and desalination with contributions of various CDRs. And here we have desalination, reverse osmosis, and reverse osmosis plus direct ocean capture. Remember, this can go with desalination as well, as docs can work with that. So various contributions, with the largest contributions here in terms of water consumption coming from food crop in no climate policy, but remains high also for these two scenarios. And here reverse osmosis and docs come up big for these two scenarios, whereas it's very small here. Most of this in no climate policy mostly rely on distillation and reverse osmosis, not caring about staying below 1.5 degrees C. Fractional water consumption for CDR to stay below 1.5, so huge consumption here in Central America and also here in South America and large parts of Russia here. So you have to understand the details. 10 to 17% of fractional consumptive water use by 2050 here goes to CDR. So obviously you have to reduce impacts, and the idea of this paper is to rely on a combination of CDRs to meet the global warming target goals while also reducing impacts on land systems, water and energy. Fractional water withdrawals from desalination. So desalination as a fraction of water withdrawals. Here you have maximum of 5 to 9% happening in the Middle East and parts of Western Asia here, parts of Northern Africa and Mediterranean countries, and parts of Western Australia as well. So nice results in terms of just looking at CDR playing with energy, water and land systems, but remember the uncertainties from IAM have to be kept in mind as well, and the assumptions going into the scenarios. Finally, looking here at sensitivity analysis and comparison with AR6 removals. I won't go into the details here, but basically looking at combinations of CDRs and various sectors, industry, electricity, buildings and so on. CO2 emissions in 2050 in terms of gigaton CO2 equivalent per year coming from four various scenarios. So below 1.5 degrees C by 2100, for example, has combinations of things in terms of the CO2 emissions impacts. High cost CCS, you have lower amount of CO2 withdrawal. Limited biomass, you end up with more emissions here. No biochar, so you have various other uses showing up with their contribution to energy. High cost weathering, so that will give you these combinations. So you have biochar, biomass to hydrogen with carbon capture and sequestration, bioliquid refining and bioelectricity. So just look at the change in colors and the contributions to emissions in CO2 equivalent by 2050. Okay, so below 1.5 C plus sectoral strengthening will require enhanced weathering to play a bigger role, just like here in no biochar and in these two scenarios. And you have lower role for direct air capture, but you have emissions from other players here. So these are the drawdowns and these are the emissions. So you have to keep in mind what combination of CDRs play a role to manage the emissions from these various sectors. Here are comparisons to AR6 results in terms of CO2 removals. Let's see, these are the number of simulations being used. Here is the range from BECS, so the model puts us here in terms of CO2 removals, and that's where AR6 would take us in gigaton CO2 per year. With afforestation, this is what you end up with, these number of scenarios. Direct air capture, so these are the CO2 removal contributions over time. This is from enhanced weathering, so those are the time scales, so going up to 2100, of course. Here is from biochar and direct ocean capture. So it's good that they're comparing to AR6, but let me not read too much. Basically, it says CDR can be beneficial if it helps avoid higher costs of mitigation, adaptation, and residual climate damages, and it will be essential to meeting the well below 2 degrees C and below 1.5 degrees C goals, alongside rapid scale-up of renewables and other low-carbon technologies. But CDR at anywhere approaching the scales projected here would require strong policy incentives, extensive monitoring and verification, and public investment in and acceptance of the associated infrastructure and supply chains. I've talked elsewhere in other podcasts about the gaps in terms of the investments for renewables and CDR technologies, just in terms of the innovation research needed to make the CDRs effective and scalable. Is still a ways to go. So we are making future scenarios based on these technological promises, which may or may not be delivered. So we have to be always cautious about those nonetheless. Okay.